All right, so let's take a look at an example. Suppose I want to know how often teenagers go to the movies. Specifically, I want to know how many times per month a typical teenager ages 13 through 17 goes to the movies. Now, suppose I take a simple random sample of 100 teenagers and calculate the sample mean. Notice how this is labeled as X bar because that's one sample, to be 2.1. The sample mean is an unbiased estimator of the unknown population mean mu. Okay, we don't know the population mean. Unbiased, remember, means it's not consistently too high or too low. I would estimate the population mean to be about 2.1, okay? However, what's going to happen is if we take a different sample, that's basically going to give us a different sample mean. So we have to think about the variation in my sampling model for X bar, because X bar, or one sample mean, is 2.1. That's just one possible point estimate. The true mean could be a little bit bigger than 2.1 or a little bit smaller than 2.1, because if I take one sample mean and I get 2.1, I take another one and get maybe, say, 2.3, those are different. They're both close to the population mean, but not exact. So we have to take into consideration the variation between the sample means, and that the population mean could be a little bit higher than the sample mean or a little bit lower than the sample mean. So now let's take a look at an example. Let's take a look at the sampling model. Remember, this is the distribution for the number of times teenagers go to the movies. This is a sampling distribution of sample means. Okay, so if I went out and gathered many, many samples, and I put all of those sample means on my graph, this would be a sampling distribution of all of those possible sample means, okay? This sampling model for X bar is approximately normally distributed. The mean of this distribution, just like we did in Unit 6, the mean of the sampling distribution is the same as the population mean. The standard deviation of this model, remember, to get the standard deviation, we are going to take the population standard deviation and divide by the square root of n. Now, we're assuming that the population is at least 10 times the sample size. You need that for your standard deviation and your independence condition. Now, what exactly does this tell us about the sampling distribution and where 95% of the values of the mean are going to lie? So all that means is, let's take a look at our distribution right here. Okay, and let's sort of think, this is all of our samples. Let's say we want to look at 95% of the curve. What information does this tell us about how far away from the mean all of these samples are if we're looking at 95% of the curve? All right, so let's see what exactly that means. We know from our simple random sample of 100 teenagers that the sample mean was 2.1. Let's say that we know that the population standard deviation is 0.5, okay? The standard deviation for the sampling distribution is going to be sigma divided by the square root of n, okay, which is 0.05 from up here, and our sample size was 100, or 0.05. Okay, so basically if we're looking at our distribution, our curve down here, we don't know the population mean, but now we know the standard deviation here is going to be 0.05. Okay, now remember from your empirical rule that 95% of our samples will produce a statistic X bar. So when I go out and I take many, 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 many samples and I put all of those samples here on my curve, 95% of the samples will be between two standard deviations above and below the mean. So remember, if I take mu and I add two standard deviations and I subtract two standard deviations, that is going to be about 95% of our curve, okay? So what that now tells us is, if I take the mean, okay, and I subtract two standard deviations, and I take the mean and I add two standard deviations, I am going to get 95% of our values are going to be within 2 standard deviations of our mean. Okay, so now what exactly does that mean and why is that important? What that means is if we were to take many samples, 95% of the sample means would be between 2 standard deviations away from the mean or somewhere in the red region. So 95% of the time, we would get a sample mean that is within 2 standard deviations of the mean. So that's pretty close. So that's basically like saying, okay, when I go out and I gather many samples and I gather all of my X bars, most likely I am going to get a sample that's within 2 standard deviations of my mean, which basically says I'm going to get a sample that is pretty close to the mean. 95% of the time, I'm going to get a sample that's a good estimate of the population. I'm not going to get an X bar out here. I may, but 95% of the time, that's not going to happen. All right, so therefore, 95% of our samples, okay, therefore in 95% of our samples, the interval between your sample minus 2 standard deviations and your sample plus 2 standard deviations is going to contain the population mean. Okay, so basically what that's saying is, let's say I went out and I gathered a sample. Okay, here's my X bar, right? And here's my population mean. I went out and I gathered this sample and I want to say, well, this is a sample, but I'm not 100% sure if that's my population mean. My population mean could be a little bit higher or a little bit lower. What that's saying then, if I take that population mean or my sample mean and I add 2 standard deviations and I subtract 2 standard deviations, somewhere within this interval that I've created, my population mean is going to be stuck inside that interval. Well, if you take a look the way I drew this, it is. My population mean is right there. It is stuck in that interval. I don't know what the exact number is of my population mean. I just know that it's basically between those 2 numbers, okay? So now let's take our sample mean that we gathered from before. X bar, remember, is 2.1. Okay, so basically that's saying let's take 2.1. Let's subtract 2 standard deviations. Okay, so let's subtract 0.10. Now let's add 2 standard deviations. So that's 0.10. And I'm going to get an interval from 1.1 to 3.1. Okay, so I apologize. I am going to change this right here. This is an incorrect answer. This should 2.1 minus 0.1 should be 2, and 2.1 plus 0.1 should be 2.2. So basically what that's saying is I took a sample mean, okay, and I extended both sides of it to say, all right, 95% of the time, I should be able to capture that population mean somewhere in my interval. And therefore, when I did that, okay, I'm now going to say my population mean is probably somewhere between 2 and 2.2. I might not know exactly what it is, but it's somewhere between 2 and 2.2. All right, so now let's continue to look at this example and see what all of this actually means, okay? So in 95% of our samples, the interval of X bar minus 2 standard deviations and your sample mean plus 2 standard deviations will capture the parameter. So like I said, okay, our population might be right here, our sample's right here, but if I add 2 standard deviations and I subtract 2 standard deviations, then notice, all right, within that interval, I've captured that population mean. I don't know exactly what it means. I just know that it's in this interval, all right? So what exactly is X bar, 0.1, and the 95%? Well, X bar is your point estimate. It's your point estimate because it's an estimate of what the population mean possibly is. It's our best guess because we took it from a sample. 0.10 is our margin of error. So our margin of error just means like, hey, we know we got this answer, but our answer could be a little bit too low or a little bit too high. It's basically how close we believe our guess is. If you have a small margin of error, you think your sample is really close to the true population. Large margin of error, really far away from the true population. 95% is the confidence level. Now, this is a tricky interpretation. It basically is saying the interval catches the unknown parameter or the unknown population in about 95% of the possible samples. So if you think about our curve, the level of 95% says, okay, here's my X bar. All right, if I make a 95% confidence interval based on X bar, I'm going to extend it 2 standard deviations. Oh, look, I caught my population mean. If I get another one right here, I'm going to make a 95% confidence interval. Oh, look, within that interval, there's my mean. So if I create 95 samples, okay, or if I take 100 samples, 95 of those samples will be close enough to the population mean that if I give myself a little error, okay, a little margin of error, I'll be able to capture the population mean. So the margin of error accounts for sampling variability. So remember, when we take different samples, we're not going to get the same answer each time. I'm going to get an answer here, I'm going to get an answer here, I'm going to get an answer here. Okay, it does not compensate for any bias or, bad sampling methods. The margin of error just accounts for the fact that when I take different samples from the population, I'm going to get different answers. Okay, so let's continue to look at this example. For our sample of 100 teenagers with our point estimate of 2.1, because our margin of error, so this is saying, hey, we're not exactly correct, it could be a little bit higher, a little bit lower, because our margin of error is 0.10, then we are 95% confident that the true population mean lies somewhere in the interval of 2 to 2.2. This is going to be a very important interpretation that you are going to have to know how to do. Okay, starting at this point right here, we are 95% confident. We're not 100% sure because we haven't gathered our whole curve, but we are 95% confident that the true population mean is going to be somewhere in this interval that I created. I took my sample mean, gave myself some margin of error above and below, and I'm 95% confident that it's going to be in that interval. Now, the interval, okay, 2.0 to 2.2 is a 95% confidence interval. Why? It's because we're 95% confident that the unknown population mean lies somewhere in that interval. We're not sure exactly what it is. We just know it's between 2 and 2.2. So what's the big idea here? The big idea here is that the sampling distribution of X bar is going to tell us how close we get to the population mean, all right? All the confidence intervals we construct are going to have the same formula. You're going to take your point estimate, which is basically your sample, and then you're going to add or subtract the margin of error in order to get a confidence interval that looks like this. So your sample mean is basically in the middle. You add the margin of error, you subtract the margin of error, and you get a beginning and ending point, all right? So a C% confidence interval, so you're going to see 90, 95, 99% confidence interval gives an interval of possible values for a parameter. The interval will always look like this, your point estimate or your sample plus or minus your margin of error. The difference between the point estimate and the true parameter, or what you gathered from your sample and the true population, will be less than the margin of error in 90 or whatever percent confidence of all samples. So all that means is basically it's saying that 95% of the time, the true population mean is going to fall somewhere in that interval. The confidence level, so you're going to see like 95, 92, 99, 85, whatever, gives an overall success rate of the method for calculating the confidence interval. So that's basically like saying if I take 100 samples, 95 of them, I'll create an interval where I capture the population mean. If I create a 92% that says if I take 100 samples, 92 of those samples, I'll be able to create an interval that I get the true population. If I take 100 samples and it's an 85% confidence interval, that will tell me 85 of those are like good samples and they'll capture the true population mean. Okay, so here's a sampling distribution for a sample mean, and let's just take a look at what this means. So 25 samples of the same size were taken, okay? So basically if we look, we have sample 1, 2, 3, 4, 5, 6, okay? There's 25 samples. We chose a 95% confidence level, and all that means is I took my sample and I added 2 standard deviations and I subtracted 2 standard deviations. The red dot is going to be your point estimate, okay? The green bar is the margin of error, okay? So basically this is my X bar, and I added 2 standard deviations, subtracted 2 standard deviations, added 2 standard deviations, subtract 2 standard deviations. This black line that we have right here, this is my true population mean, okay? Now, if we take a look, when I have all of these samples, okay, if we notice, every single one of them contain the true population mean. So we did a pretty good job, except one of them. Take a look at this one. Sampling variability says, hey, this sample was a little bit higher than the population mean. So when I created this interval, I didn't quite get the population mean. So that's going to tell us that 24 out of 25 samples captured the population mean. And if you do that on your graphing calculator, that's 96%. So 96% of the time I got the population mean, and 4% of the time I did not, which is okay. We're not perfect. We didn't get it 100% of the time. All right, so here's a sampling distribution for a sample mean. So we already answered this question. How many confidence intervals miss the true mean? Well, just one of them, okay? Only one was like not a good sample. And that's basically saying after you took many, many, many samples, how many got the black line within the interval? Well, all of them did but one. So 24 out of 25 were good sample collections. All right, so if you would like to take a minute and go to this website right here, you can take a minute, go to it, and just play around with your confidence intervals and see what happens when you take different sample sizes, okay? So go ahead and take a second and just follow the directions on this page. And I just want you to look at what happens to the confidence interval size when you go from 99% to 80%. What I want you to notice is that the confidence interval gets larger when the confidence level increases. And that makes sense if you think about it. If I have my sample mean and I say I want to capture it 95% of the time, that's going to cover 95% of my curve, which is more than 80% of the time, which is 80% of my curve, which is a smaller proportion. All right, now the next thing I want you to do is kind of mess with the sample size, all right? So I just want you to take a look and see when you gather different sample sizes, what is going to happen to your margin of error. So I want you to think about this. As you increase the sample size, it's not going to affect the confidence level. Okay, it's not changing the fact that I'm going to capture 95% of the time, 85% of the time, etc. Okay? The intervals become shorter the larger the sample size. And that's because, think about that, the more samples I have, the more I am closer to the true population mean or proportion, because I have more samples, I have more of the population, and it's actually going to decrease the standard deviation. I'm still going to capture it 95% of the time, it's just that my interval is going to shrink. All right. It is incorrect to state that increasing the sample size makes us more confident. It doesn't. Our confidence level stays the same. Increasing our sample size makes our estimate more precise. Okay. So basically that's saying maybe we're going from 2.0 to 2.2. I make a bigger sample size, and maybe I'm going from 2.05 to 2.15. So more precise is going to tell us, hey, this is a smaller interval, so I have a better idea of what the population mean or proportion is. Okay, so just this is a big thing for the AP exam. Please make sure you are using this wording correctly. Every single time that you create a confidence interval, you must use this first wording. Sometimes it will ask you for the confidence level. So when you interpret a confidence interval, this is what you must say. We are blank percent confidence. We are 95% confident that the interval from, let's just say 2.1 to 2.2, captures the actual value of the population number of time teenagers go to the movies. You have to put that in there. This is, you will use this over and over again. You're literally just going to fill in the blank for here and here and here and here. Okay. Now the level is basically telling us what we're doing. Okay. Our level is going to say, if we take many, many samples of the same size, 95% of them will result in a confidence interval that captures the actual parameter value. You might be asked to interpret the level. The level is what we're doing. Okay, if we take many, many samples, 95, 85, 75% of them will create an interval that actually captures the population value. Okay, and here this is saying, hey, we're 95% confident. We're confident in our methods that we created that the interval captures the true population mean or proportion.